have not actually done the work to make a proper synchronized timing loop to drive our game. So we could go ahead and make our game on the platform layer that we have now, but we would be at risk of having greater audio latency than we should have. We would be at risk of sort of having just synchronization problems there. We just haven't quite gotten to the point where we really understand the timing of when things show up on the screen and when the audio plays out the speakers. And so I'd like to do a little tightening there before we even start. I know I've said later that we're going to go and have a pass on the Win32 platform layer when we're going to ship, where we do a bunch of things that we've been putting off that are performance kind of stuff, that sort of thing. And compatibility stuff that we're not addressing now. But this I want to address sooner rather than later, because all of the decisions that we make in the actual game itself are all driven off of this timing. So when we are playing the game, when we are deciding how long things should take in the game, every last thing we do is going to be based on excuse me, is going to be based on whatever that clocking is. So if we have that clocking wrong in the platform prototyping layer that we've got now, then we're at risk of making a whole bunch of tuning things incorrect in our game. And then when we go to finalize the platform layer and tighten all that stuff up, then we have this problem where, oh, now all the tuning values, that all of the stuff that we tuned in our game and all of the stuff that we thought was right for playability of the game as we were developing it is actually all wrong. So what we want to do is just take a little bit of time now to go through and kind of make it a little more coherent what it's trying to do, and make sure that we understand that so that we can know that we don't have any critical problems that will lead us to make a bunch of bad decisions that we have to kind of redo later. Anyway, yeah, someone on the stream said don't forget to start recording. The problem there is all along the piece. So if you're looking at starting actually the goal we're trying to do. Now, I took some recommendations from folks, something that they use on Khan Academy or something like this. Using the paint seems to be basically just this better, but you know what? We'll give it a little shot. That diagram sort of that I've been using for quite some time, where I'm talking about the various frames, when they're computed, when they're displayed, that sort of thing. So I'm going to make some tick marks on our timeline here, like this. And basically what we have here is this is t going forwards. This is time. This is our timeline, right? And the timeline, you know, can I get that a little smaller? Timeline. Did that get smaller? It didn't feel like it got much smaller. I don't know. Did you guys think that got smaller? Hard to say. Let's go even smaller than that. Timeline. You know what? This is just not very good. I don't know about this program. We'll give it a little more. We'll give it a little more time, but I'm not optimistic that this is actually, you know, good. Yeah. What can you do? Something we can address a little later, perhaps. Anyway. Basically, if we take a look at what happens here, we start the game at some point that we'll call T0, right? And basically, this is when the game actually begins running. So the person runs the executable, and we got to do our Windows startup stuff and all that sort of thing. Now, at some point, we actually start the timing. So we actually take a look at what our timer value actually is. And that was query performance counter was the thing that we were using to measure time. We're going to take a look at what that timing value actually is. And when we take a look at that, that first timing sample we take is going to be the first benchmark that we have for figuring out how much wall clock time has elapsed during our code. So I'm going to call T0 that actual time. That is our first look at query performance counter, right? That's our T equals 0. Now what's going to happen there is during this first interval, during this interval here, right? During that first interval, we are going to be displaying essentially nothing, right? This is just plain blackness on the screen. We will, if anything, we just have a cleared window. There's nothing there because we have not actually prepared any actual anything really. We haven't actually got a frame buffer that we can show. So extending backwards as far as time goes is some sort of blackness. And then there's going to be some tick mark that's the first tick mark where we actually display a frame. Now, if we want to, we can also call this T0. It depends. This is, again, we're going to have a bunch of decisions here. We have a bunch of decisions. We could also call T0 the first frame flip, right? We could call it here, right? So I don't know which one we want to call T equals 0. We could call it the start. We could call it here. Hard to say. Something we're going to have to decide in a few minutes. But basically, at some point during here, inside here, we are computing frame 0, right? We are computing frame 0, audio and video, right? We've got both of those coming online. So we're doing the computation work inside this time interval to compute those. When they are done, we will then flip them so that right here and coming forwards to here in this interval, you can actually see frame 0 displayed. So on the screen, you will see frame 0, right? And ideally, what we'd also like to do is have audio 0 show up right along with that, right? So we want audio 0 to come right here as well, right? I don't know how you guys feel about slashes through 0. Sometimes I feel like it's a little classy, you know? It feels a little European, a little fancy. So maybe I'll just go ahead and put that in there. Put that in there. So, what we've got now is we've basically got a time interval. This could have been as long as we wanted, right? Because blackness is on the screen and no audio is playing. So this is silent blackness, right? Sounds like some bad sci-fi movie. Silent blackness is here. And then once we start here, we have both audio and a frame on the screen. So what basically happens is this can be arbitrarily long. This time interval is arbitrarily long, and we don't actually care how long it takes. It could take an hour. Well, I mean, we care about that because we don't want to keep the user waiting, obviously. But it doesn't matter how long it takes because there isn't anything actually being displayed. So as far as the user knows, they're not going to see any glitches or hear any glitches if this takes too long because there's actually nothing going on. It's just starting up. The window has just come on screen. But once this is going to be on the screen, this is basically a fixed duration here, right? Oops, that's not very good. This is basically a fixed duration that we have to compute the next frame. Now, I want to really underscore why I say this is fixed duration, because there's a lot of stuff, like, I don't know if you guys have seen, NVIDIA has made some announcements, and there's been announcements on like other standards and stuff about variable frame rate displays, right? Excuse me. Like the kind you would normally see from just today. Normal monitors have some frame rate that they update the image at. And so that frame rate, whatever the monitor is updating at, is also what we would like to update at. If the monitor is refreshing the image, right, at 60 frames a second, so that's, 16 milliseconds or so, 16.6, something like 17 milliseconds a frame, right? If you think about that, we want to synchronize with that presentation. Because if we do something other than 60 milliseconds a frame, then we will essentially be off beat with the monitor. So if you imagine the monitor has kind of a timeline down here as well, if it was updating at a different rate than we were, let's say a little bit less, like this, right? Of course, I don't know if I gotta get that out of my head. There we go. Basically what will happen is eventually we'll miss a frame. So right here it won't matter. Here it will display this frame. Here it will display this frame. Here it will display this frame, but here it will display the same frame again, the monitor will. And we'll have to wait till a much longer time than the user has used to been seeing. It's used to seeing this interval. Now it's going to see this interval, and we're going to see, we feel like we skipped a frame to the user. So we want the monitor's refresh rate and our refresh rate to be the same, right? We want to update at roughly the same frequency so we're consistent so that every time the monitor goes to get a new frame, we give it a new frame. That's the goal. So we can do that on either the monitor's actual refresh rate, like let's say it's 90 hertz or 120 hertz monitor. We can do that at actually 120 hertz, or we can do it as some subdivision of that. So let's say we're updating our game at 60 frames a second, and the monitor is 120 frames a second, 120 hertz, 60 hertz. Hertz is just cycles per second. Well, as long as we're a multiple of 2 or something, an even multiple, 3, whatever, away from that, then we know that we're never going to hit that beat frequency problem where we're going to have problems of skipping a frame as far as the monitor is concerned and having the user see a apparent change in animation speed. Sorry. I made some homemade almond milk today, and I didn't do a very good job. It's kind of rough, and it kind of scratches your throat a little bit. I don't know how to fix that exactly. I got to think about it. I'm still new at making almond milk, so yeah. What are you going to do? It's not the store-bought brand. So, all right. Basically, what I wanted to say about that is that there's a lot of talk now about variable refresh rate monitors, and basically what those are monitors that can update at whatever frequency you want, for the most part. So basically, what happens is whenever your frame is done, you just say display the frame, right? And so you might say, well, why do we care about any of this? Isn't the future going to just be you take as long as you need to display the frame, and then you display it? Isn't that fine? And I don't understand the attraction of that. To me, that just sounds absolutely awful. I do not understand why anyone would ever want such a monitor at all. And the reason that I say that is because I feel like it always forces you to be completely wrong with how you displayed your animation. And the reason I say that is because imagine how the computation cycle goes on one of these variable frame rate monitors. Well, I come down here, right, and I'm basically saying that I'm going to use a variable frame rate. So it looks something like this. Who knows what it looks like. Let's say it looks like that, right? So we've got something here. Let's say this is going to be, something like 30 milliseconds. This is going to be something like 16. This was like 20, right? And this was back to 30 again. So we have a completely variable thing here. So what happens, we know that 30 milliseconds has elapsed. These are milliseconds here. We know that 30 milliseconds has elapsed between here and here, right? Something was on the screen here. We don't know what it was. We're saying this at some point in time. So it was with the previous frame. Who knows what happened? So let's talk about starting here. Well, we know that the world updated 30 milliseconds between here and here, right? We know that 30 milliseconds of time has gone by. So we need to tell the physics engine for whatever frame is that we're going to display right here, we would want to tell it 30 milliseconds because there is a state of the world here, right? This is world state 0. This is world 0. And now we need to display world state 1, right? We want to render what the world looks like 30 milliseconds into the future, okay? But there's a problem. We don't actually know this value yet. Because we have a variable frame rate monitor and we're going to flip whenever we're done, we have no idea what the 30 milliseconds is. And most of this time is usually rendering. Like this is rendering right here, right? So the physics happens somewhere in here. It's got to know right away before we even have any idea how long the frame rate is. It's got to know how much to update the world by. How does it know to pick 30 milliseconds? Well, it doesn't. So it probably looks at the previous frame for a guess. Well, if it looks at the previous frame, it's always going to be wrong. It's going to look at 30 milliseconds here, but surprise, this took 16 milliseconds. So now you've got a world that appears to be moving twice as fast. Then we go here, we look and it actually turns out to be 20, but we thought it was going to be 16. So this is actually a world that appears to be moving slightly slower, blah, 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 right? So I do not understand. I do not get it. People who believe in this technology, please feel free to write in and tell me what the attraction is, because I do not see it at all. As far as I'm concerned, you need to know what you expect your frame rate to be in the future, and you need to guarantee that you're going to hit that frame rate in order to get a smooth, believable looking, non-hiccupy sort of animation. unless you just don't care, you know? And so this, I think, is very important. So what I would say is variable update monitors might be useful if your frame rate, if you can guarantee your frame rate, but you happen to know it's always 45 milliseconds, let's say. Of course, that would be pretty bad. So let's say it's something like 20. You know, it's always 20 milliseconds. Well, that's fine then, as long as you're fixing that rate. But really, a variable refresh rate monitor doesn't actually help you during the course of your game. What all you really can use is something that's essentially a fixed rate monitor where you can set the rate. And so that I think is kind of mostly all I wanted to convey about that. Is I don't really understand the attraction of those things much at all. And I think if anything, they're only good because they allow games to run at other fixed frame rates that aren't 30, 60, 90, basically. Maybe you can get, you can use 70 or something. And maybe you couldn't do that before in any realistic way. So I don't know. Just something to think about. Want to get that out there. So maybe I'm thinking about it the wrong way, but that's always been my problem with that whole concept. So for me, whenever I do a game loop and I'm looking at timing stuff, I always want to have a target frame rate, and we try very hard to hit that frame rate. And if for some reason we're not hitting that frame rate, we pick a new lower frame rate, and we're always trying to stay fixed at whatever that frame rate is. So if we're trying to run at 60 and we can't run at 60, we drop down to 30 or something like that. And again, maybe that's where these variable frame rate monitors could come in. They allow us to change our fixed frame rate. But I never want the frame rate to be variable. I never, ever, ever want that, because there's no way to actually make that work properly. Your physics is always wrong if you do that. So what I want to do is I want to make a frame loop that basically obeys this sort of thing, where it's going to have an opinion about the frame rate it can hit, right? So it knows how many milliseconds that is. We'll call that the target milliseconds. So we know what our target milliseconds is, right? The target millisecond comes in, the physics updates the world, right? So we get our update here. It's the target milliseconds drives our update. We do our render. And then we do our page flip of that render right as close to the boundary of the target milliseconds as we can, right? Then we do the same thing over again for the next thing. And now this may be pipelined. So remember, this may go off to a GPU or something, which actually delays everything by a frame while it chews through it or whatever. That's fine, as long as we are always pushing it at a synchronous thing, and we set it to synchronize, say with the vertical blank or whatever, the monitor refresh, we'll still be just fine, as long as we always know that we're updating with a particular target in mind, and that target matches our flip rate. And that is what we're trying to do. Now for the audio, we have a slight other problem here. The problem with the audio is, ideally what we'd like to do is feed just exactly the amount of audio that we need every frame. But if we do that, we do run the risk of, if we miss, like let's say we missed for our 30 millisecond time, right? So we actually missed, and we're going to have a frame lag. Well, our audio would skip here. So we have two choices, because we basically need to make sure the audio is always there on time. We have two choices. Always get the audio there on time, meaning our frame rate is a hard constraint, and we've basically written the game to never miss frame rate. The other one is always feed the audio somewhat further ahead. And there's two methods of doing this. One method is just to be a frame of lag off, right, or something, or half a frame of lag off, right? In order to handle a whole frame miss, you kind of got to be a whole frame of audio ahead, right? So that would incur 16 milliseconds or 30 milliseconds, depending on the frame rate. This is at 60 hertz, and this is at 30 hertz. I should probably start saying 17, because it's 16.6 repeating, right? It's 1,000 divided by 60. But you know what I mean. When I say 16, it's code word for 17, 16 and a half, whatever. You know what I'm saying. Anyway, basically what happens here is I'm introducing audio latency, so I could try to reduce that audio latency by doing one of two things. One thing I can do is always feed 2 frames of audio, but when I do hit my target, when I do find that I wake up and I've got plenty of time to update the audio, so I'm here and I go, okay, I've got plenty of time to update the audio, update it as overwrite the old stuff that I wrote, right? So basically, always give it an extra frame, but don't use that extra frame if we have time. We'll just splat a new one, right? That's one way of doing it. Another way of doing it is, like I said, to just always actually write one whole frame ahead. And a final way of doing it would be to have like a thread or something that's sitting there waiting, and it looks to see if we've updated by like right here. And if we haven't, it emergency flushes another frame of audio, right? So it's kind of like a guard, right? So we got a couple options. We've basically got one always hit, we've got always hit the frame rate. We've got overwrite the frame, overwrite the next frame. We've got a frame of lag, and we've got a guard thread. And there may be even other methods. Those are just the ones that I happen to know about and have ever seen used or used myself. So I'm not 100% certain that I can honestly argue directly for any one of these in particular. It's kind of hard to say. I think the one that I would rather go with, because it's simpler and it enforces sort of a little bit of discipline, would just be going with option one. Option one is the easiest option, is to always hit your frame rate, right? And one of the things that's interesting about that I like is I like the mentality of saying that this game has to hit its frame rate instead of just allowing it like, oh, it kind of gets slow sometimes and we don't want to optimize when the explosion happens or whatever and it gets slow, so we'll just let it get slow there and we'll compensate by having the frame rate looks crappy but the audio doesn't skip, so we're happy, right? I don't love that. I feel like if we write a game and the user is being reasonable, so they're playing our game and not running like another game in the background or something where they deserve to hear some audio skips if that's where they're going. I would prefer kind of to say we always hit our frame rate. So, we target 30 hertz, let's say, and we always get there. And if we don't hit 30 hertz, then that means we have to optimize whatever it is that's making us not hit 30 hertz. So I'm tempted to go with this one first. I think that might be which one I'd go with first, but I wanted to mention these other ones because maybe we'll have to switch to them if we find that we're unsatisfied with what I'm talking about here. Or you may choose when you're implementing this basically to go with a different option because you care about different things. Because many things in programming, there's not a right answer. There's simply a question of your priorities, and those priorities will lead you to make a certain decision or a different decision. And you can't really say that the decision was wrong or right. You can only say if it was wrong or right based with respect to some priority system. So there you go. Hopefully that makes some sense. So we need to do a couple things that we're not doing right now in order to make this happen. The first thing that we're going to have to do is we have to figure out some way of knowing or at least getting some idea of what the monitor refresh rate even is, because we want to run at that refresh rate. And so we kind of have to go ahead and take a look at at ways to figure out what the refresh rate is of the monitor that we're actually using. Now, to be honest, I haven't done this in a long time, and I did write down some notes about how I used to do it, but it's going to be a little dicey, and the reason for that is I don't really know all the stuff that happens essentially with multiple monitor scenarios. So if you take a look, basically here's the thing that I was thinking about. You can actually see get monitor refresh rate. Let's just take a look here. Where is our MSDN? MSDN, here it is. Let's take a look here. I'm pretty sure that some of these are just not actually, well, okay, this might work. So this might actually work because it does take the HDC. So we'd be able to pass our Windows device context handle. And let's see if this is going to be something that we think is a reliable value. I don't actually know if it is or not, but we can sort of see. So here we go. The current vertical refresh rate of the device in cycles per second. So basically this, a vertical refresh rate value of 0 or 1 represents the display hardware's default refresh rate. So that's not really useful, right? That's not going to tell us. We actually need it to say something like 60 or something like that. That's if it's just going to tell us something nonsensy like that, that's not going to help us. So we can enumerate. We can also enumerate the monitors, try to find it from there. I'm not entirely sure. I'm not entirely sure what the best way to do it is nowadays. This is a good question, and I'm not super prepared to answer it. So yeah, I don't know. I don't usually trust the Stack Overflow answers. I found them to be wrong a lot of time, so I don't tend to look at these very often. And this doesn't look particularly convincing here either. So I don't know. I'm going to go ahead and say that I'm just going to go with enumbing the monitors. This is the kind of thing that I do nowadays, and I haven't really played around with refresh rates too much, but I just want to kind of, I feel like this might be the most useful way to go, because I think this will probably give us a way to get it. So I'm going to take a look at this. Basically, enum display monitors is the thing that allows us to see basically all of the things in the system that are monitors that can be displaying graphics, and I believe we can do a pretty easy way to actually get the one that we're on as well. So let me take a look at this. Then when we call get monitor, we can call get monitor info on those, and I believe that sort of thing will be able to allow us to ask for stuff about the refresh rate. I'm not actually sure that that's actually true, but I think it might be. So let's take a look here. Monitor info. Yeah, we can, let's see, still not the case. Let's see, get refresh rate of H monitor, because I'd really like to be able to do it from here if possible, because I just don't actually trust the other thing. Yeah, so you can, yeah, I don't know. I'm sorry I'm hemming and hawing so much here. I just, this goes relatively easily from the monitor, and whether that gives us back, I'll just test it, whether it gives us back the actual information that we want. It looks like it probably would. So let's take a look here. Height, display frequency, right? So is that defined? Let's see what MSDN says. Again, MSDN can definitely be wrong, but it's usually my first go-to. I trust it more than Stack Overflow anyway. So let's take a look here. Frequency. What that basically says is this value is also known, blah, blah, blah. When you call this may return with value 0. What is with this 0 and 1 thing? Well, all right. I guess I'm not sure what way I can really definitively say what the monitor refresh time actually is. It does not seem to be something that's forthcoming. So I don't know. That's kind of disappointing to me. Normally, so I mean, just to be clear, the reason that this doesn't normally come up is normally what happens in OpenGL Direct 3D is you set them into a mode where they flip on the monitor refresh anyway. So when you do that, all you have to do to figure out what your refresh rate is time how long it takes to flip in one of those two things, and then you roughly know what the graphics card is doing. That's pretty straightforward and not that difficult. But in this case, if we actually want to know, because we're doing the flip, we're doing the blit ourselves, so we don't really have that freedom, the way you would used to do it is with direct draw. But direct draw is kind of old and deprecated. I don't know. We could try to do it. Direct draw, get vertical refresh. This is the way that I used to do it in the old days. We could try to do it. I don't actually know whether that will be sort of whether that will actually be accurate though when we ask for a particular monitor's vertical refresh. So let's see what it actually says here. I don't know what this is. This is some crazy stuff here. Let's see. Anything particularly interesting here? No. This looks totally off the rails. This is the MSDN page, but it's for the flip call. So I don't actually know if that's something particularly useful, and it's Windows Mobile, so that's not going to do it. Yeah, I don't know. This may be something we'll have to save for tomorrow, and we'll just have to put in the value. I'll go look at my old code that uses direct draw, and we can try it, unless there's some better way to do it that we can find, because we can't really, if we can't rely on one of these things to not give us back 0, 1, I'm not sure what we can really do, because if you look at, like, I don't know, if we look at this code, it doesn't look particularly useful. There's really nothing you can do there. The default refresh rate is not something that seems to be defined anywhere. So anyway, excuse me, we'll have to tackle that tomorrow, I guess, and I'll do the direct 3D version. I'm sorry, the direct draw version. I don't know what else. Oh, that's not the command prompt we want. We have our own custom command prompt. There we go. Well, that's disappointing. I was hoping that there would be an easy way to get it, but it looks like there isn't. That's the sad state sometimes of operating systems. Something like getting the monitor refresh rate should be just like one call. You're like, here's the monitor I'm on. Tell me what the refresh rate is, and it should guarantee to give you back the refresh rate. and I do not know how we get into situations where that is not the sort of the standard thing to happen. But you know, what are you going to do? That's just life as a programmer in the platform layer. It's one of the reasons we'll be very happy to get off the platform layer next week, so we don't have to deal with stuff like this. All right, so basically what we're going to have to do is we're going to have to assume that we make up a refresh rate. And so for now, we'll say that there's a refresh rate up here. We'll say that this is a refresh or monitor refresh hertz, and that will be just 60 for now, right? So we'll just say it's 60 refreshes per second. And we'll say to do how do we reliably query this on Windows, because we don't know. Maybe direct draw is still the way to do it, which would be kind of scary because direct draw is deprecated. So that would not be my preference, but what are you going to do? All right. So then what we can do is from that we can compute some synthetic values, right? We know that from that we can compute how much time we expect to go by in seconds for every frame. So basically the seconds elapsed per frame, right, is going to be the milliseconds, 1,000 milliseconds per frame, divided by that monitor refresh hertz, right? That's going to give us how many seconds are elapsed every frame. So I guess the other thing we should say is we have a game update hertz as well, right? And I sort of was saying that we probably don't want it to be the monitor refresh rate because we're going to not probably hit 60 when we're doing software rendering. So maybe let's say this is 30 as well, and basically we'll derive this from this once we actually get to some place where we can get this value. So you know, for now we'll say it's that divided by 2 or something like that. So really, the second elapsed per frame is actually going to be our games update hertz because we'll probably be only flipping every other time. So that's how much we want to actually have elapsed. So the first thing we need to do is actually measure this, which we already kind of put in the basis of, and then we want to actually wait until we get to the point where we're at this time elapsed, and then we can go ahead and sort of delay, if you will, our page flip to just the right time so that we get 60 frames a second. Or in this case, 30 frames a second, whatever our game updates hertz is. So what we want to do is down here somewhere, right? After we've done everything, remember we have a thing, we already kind of put a thing in here where we query performance counter. So we know how much time has elapsed, and we were printing that out before. We were printing that out right here. So we basically have a value, which is the counter elapsed, and we actually did the milliseconds per frame thing here. And so what we want to do here is change up what we're doing a little bit. What we want to do here is say how much time has actually elapsed so far, right? So seconds elapsed for compute, basically, for work, let's say, how much we actually had to do. And we know what that value is. That's this right here. So we're going to go ahead and do that. And that's just this particular thing. We don't actually care about this, the 32-bitness, I'm sorry, the 64-bitness of that, because we've already done the subtract. So that's all good. So once we do that, we basically have, and we don't need the 1,000 anymore because that was to compute milliseconds. So really all we need to do is divide the time that elapsed by the frequency of our clock, that Windows reported for our clock, and that will give us back how many seconds elapsed during the work that we did for our frame, right? Now what's going to happen here is that's going to be different than the other value, the value that we basically computed up here, which is how much seconds we want to elapse per frame. So this is the seconds elapsed per frame target. And we could actually call that target seconds elapsed per frame, or target seconds per frame, something like that, right? So we have a target seconds per frame, and we're going to see like basically how much time we have left. So assuming we're always trying to be under it, right? So we're assuming that we essentially have, we almost want to have sort of a while loop here, right? We want to kind of say while the seconds elapsed, we could even think, yeah, in fact, I'm going to change this back to so far because we could just go ahead and, no, you know what? Because we're going to want to print that out. Never mind. I'm going to save it that way. That was good. So I'm going to do seconds elapsed for frame, right? And we'll start that off by saying we're going to actually be doing this query performance counter. We're going to be doing this actually inside a loop. So we're going to take a look at the seconds elapsed for work. We're going to say that we're going to start with that. And then we're going here and say if the seconds elapsed per frame is less than what we actually wanted. So if it's less than the target, right, then we're going to take some action to basically make sure that we are not going too fast. So we're basically gonna slow things down. So the first thing we can do, and this is just the CPU melting version, is we can just do this again, right? We can just go ahead and full on do this sort of thing. Now you can see that this is going to start to get messy if I keep doing something like this, where I keep, I keep checking and checking and checking. So we're going to probably want to pull this out into utility function, but for now, we should probably be fine. So what we'll do is we'll just keep getting the end counter over and over. We'll look at the counter elapsed, and then we'll basically do the seconds elapsed for frame computation. We'll just do it inside this loop, right? We'll just keep on doing it and doing it and doing it. And so what we should do, oops, don't want to define that again. What we basically should do here, and you know what I can even do? I don't even need to do that. I can just stick that right in there. There we go. And make that divide a little clearer. There we go. So basically what we can do is just keep on doing this, and until we get to the time when we actually get above the target seconds per frame, right? And then we can go ahead and do our flip. So in theory, if we actually do that now, in fact, we should actually, that should actually just be basically a locked loop that forces us to update at 60 frames a second. Now we'll have to verify that that's actually true, but let's just go ahead and make that happen here. Where are we? There we go. Let's see. Why am I not getting any input here? That does not look reassuring. I feel like we should be getting some input, but we are getting no input whatsoever. That doesn't sound good. Something has gone horribly, horribly wrong. I suspect that probably this while loop was busted. Hold on 1 second. While seconds elapsed per frame is less than target seconds per frame. Nope, that should be... What did I do wrong? It was off to a good start in the stream today when the first thing I type in is already lousy. But you know, programming's like that some days. Some days you're on and some days you're off. And on days when you're off, it just means you got to do a lot more debugging. And you know when it happens. But you know, what can you do? You gotta chin up, you know, and get through it. Anyway, let's go in here and step in the debugger. Hopefully it'll be relatively obvious what I messed up there, because we're not actually updating. So I think what's happening is this while loop is never actually making this get big enough for what it should be. So, oh, well, that was easy. It looks like we left yeah, that's good. That's stupid. All right. What I basically did there is I computed the target milliseconds per frame instead of the target seconds per frame. So that's pretty much the entirety of the bug. Not particularly interesting, to say the least. So, okay, in theory, we should actually be going at somewhat more of a consistent frame rate, but I don't actually know if that's true. We should be going at 30 now, but I'm not sure if that's true. That audio is skipping like crazy, so I'll have to take a look at what's going on there. So let's take a look here at that while loop, make sure that's actually running properly. Oh, so this is wrong as well. So this end counter has to actually be done outside. So let's go ahead and pull. I don't know if you could see what was happening there, but basically we need to update our last counter to be proper. I mean, the fix is very simple. It's this right here. But this code is now super messy, so I'm going to go ahead and pull that out. Let's see if that makes it a little bit better. Okay. Yeah. So that looks more correct. All right. But this is still super ugly here, so we got to pull this out. So let's start by pulling out this can be always accessed. Since we compute it once, I want that to be just like a global variable that's just whatever the frequency is, and we initialize it at startup. So what I would like to do, at least, is have this variable basically, right? I'd like this to be a global. So I'd like that to be a global variable. So the perf count frequency is basically going to be this thing here. Let's see that we had it at before, perf count frequency. So basically we just want a global variable that always lets us know what that frequency is, so that we query it once and then we can use it outside in a different context. And so then what we have is we basically have our excuse me. We have our actual call that does our computation. We want that to be something that's kind of nicely encapsulated, so I'm just going to pull it out here, and I'm basically going to have a way of saying snap a counter in various places and then take a difference of them. So basically, I want something here, which is basically, it's just an inline function that's going to do get seconds elapsed, something like this, and it will take two different computation properly. It'll know that basically whatever the elapsed time is here, it'll do end dot quad part minus start dot quad part. It'll do this reliably, so we know we don't have a typo or anything in it. We can debug it once and make sure it's right. So that's fine. And then we also will have one which is basically just a way to get a clock value. So win32 get wall clock, basically. That will actually do this query performance counter and just return that value directly. So that way at least we can see it's a little clearer what we're actually trying to do with it, and we can go ahead and return that. There we go. So now we can replace our stuff with this, and hopefully it will all be good. So perf count frequencies there. Let's go ahead and put this up with our globals, and we'll call that global perf count frequency. So perf count frequency. And that should never change during the run of our program, so we should be good to go. Now, in here, we need to replace our all of our stuff that we were doing for query performance counter. What we actually want to do here is say, okay, our last counter is equal to win32 get wall clock, right, like that. And we can leave our RDTSCs for now. We're going to do something else with those later, but RDTSC is very processor specific, so you can't really use that for timing. You can't use that for timing that runs on the user's machine. You can only use query performance counter for actually timing code for profiling, because how it behaves varies from CPU to CPU and all sorts of other stuff. So you don't want to ship a game that uses RDTSC for actual game time. All right. So then we get down here, we can say this is basically our work counter. So our work counter, win32 get, so we have our work counter there, and we want to know our seconds elapsed, our, let's just call this work seconds elapsed, like that. We can say win32 get seconds elapsed, and we'll give that between our work counter, basically, work counter. So I think that's roughly right, what I want to do. Then I'm going to go through here, and this is going to be our work seconds elapsed, right? We're going to go through here and say we're going to update our check counter, basically, and that's going to get the wall clock time here, get wall clock, like that. And then we're going to get the seconds elapsed, win32 get seconds elapsed, and we're going to try to time in between the last count. Having functions encapsulate our stuff is nice because it just makes the code so much more readable, right? So we can basically just sit here and keep going. In fact, we could even be even more ridiculous if we really wanted to and put that expression right here, but I don't think we need to go that far. That doesn't seem useful, so let's not do that quite yet. Anyway, I'm going to if zero out all these things for now because we're not dealing with them at the moment. Then at the end here, at the very end, we need to update our last counter. So basically what we can do is we can say that our end counter here, large integer end counter equals win32 get wall clock, which is what we wanted. And then we can set the last counter equal to that. Now this guy here, I'm going to leave all these guys together and stick them down at the very end. This stuff needs to probably be cleaned up a little bit, but yeah, let's move all that down there. Okay. So that should be about right. I think that looks about right. Now, of course, the problem is at the moment, we don't really have a good way to tell even whether, like, what we're even running at. Like, we have no actual way of knowing what our actual frame rate even is. And so that's a little bit of a problem, to say the least, when you actually look at it. Does it look consistent now? Oh, sure, right? But how do you really know? And so what we kind of want to do is probably have some way of actually trying to verify that. And one thing we could do, and I think this is probably what we should do maybe in the remaining time, is put a little counter that just goes up every frame that we can actually time with, like a stopwatch or something, and verify that in like a minute's worth of time that it has actually gone up by the amount that we should think that it should, right? By, 60 times our frame rate, so 60 times 30 or whatever it is. But maybe, I don't know, maybe we'll do that tomorrow. We're getting kind of low on time here, so let's just keep going with what I was talking about here. So what we do want to do is we kind of want to say here, even though this is while loop work will work just fine, there's a couple other things we want to do here. First of all, excuse me, what we do want to do is we want to actually verify that we didn't miss a frame. So in the if seconds elapsed, what we'd like to do is put an else at the end of this while, right? But you can't actually do that in C. So what we want to do here is say, okay, if the seconds elapsed per frame was actually frame rate. And so this is something we want to do here that says missed frame rate, that's that. And we could even do an assertion here. But the problem is the assertion would lock up. So what we'd really like to do is this will be a thing that we'll log, and we'll be able to see that actually pretty soon. I don't know if we'll do logging next week, but pretty soon we'll be able to start seeing some of these things that we wanted to log, but we don't have a system for yet. So the other thing we want to do is this will basically just melt the CPU, if that makes sense. Basically, even if the CPU did all the work that it needed to do for the entire frame in a millisecond, it's still going to sit here in this spin lock doing a ton of work, constantly checking the performance counter, right? It's just like wasting CPU time. So what we'd rather do is we'd rather see if there's any time left that we can actually use to just sleep. Just tell the operating system to put the CPU to rest or do other work that it has to do. So what we'd like to do is use this command from MSDN, sleep, which basically, excuse me, which basically just takes a number of milliseconds and it waits. It basically just waits for that number of milliseconds. So what we would like to do here is basically say, let's do that sleep for the milliseconds, sleep milliseconds basically, right? And so in here we're going to say that we have a sleep milliseconds, and the sleep milliseconds is going to be how many milliseconds we could afford to sleep, right? We're going to say, all right, we'll take the target seconds per frame, okay, like that. We'll take the seconds elapsed per frame, we'll subtract them, right? Why did that not copy? There we go, seconds elapsed per frame. We'll multiply that by 1,000, right? Because this is in seconds, and now we've got milliseconds, and that's how many milliseconds are left, right? That's how many milliseconds are left to wait. What we want to do now is that's going to be a fractional value, obviously. Excuse me. And so we only want to, we basically want to truncate that, if that makes sense. We want to sort of, oh, you know what I forgot too? I forgot this right here. There we go. We need to actually wait to display the frame. This would actually have displayed the frame and then waited, which is not particularly useful. So what we want to do here, is we want to go ahead and see how many milliseconds we can sleep. So to do that, we're going to go ahead and truncate this fractional value. We're going to truncate the fractional value out to a D word after we compute it. And so that will give us how much we can sleep, and then we will sleep. Now there is a huge problem, though, with doing this, unfortunately, which we probably won't see when we run it here, but it's there. You'll just have to take my word for it. Oh, well, you can kind of, you can, no, you can't really see it. And it's something that's hard to see when we don't actually have something running, and when you're not in certain circumstances and whatever. Because there's a whole bunch of stuff that ties into this, but we'll get to those in a second. The problem is that basically this sleep function in Windows has a certain granularity with how long it can actually put your thread to sleep. So if it decides when you call it that it's going to put your thread to sleep, meaning your thread will no longer be executing, it is going to wait for the next scheduler granularity to wake you up. Now what that means, for those of you unfamiliar with operating systems, is inside every operating system there's some code called a scheduler, and a scheduler is what decides when threads run, like when different processes run, when the threads run. It's basically the thing that makes your operating system preemptively multitask. It's the thing that lets you run a bunch of different programs at once, and it doles out the work, it doles out the CPU time to each of these programs to allow them to do the work, right? But what happens is that scheduler basically has to be sort of a thing that interrupts what's going on. If you imagine you have one program running and you need to let the CPU do some work on another program, then the operating system, you imagine, has to like interrupt, right? It has to jump in and say, okay, stop the process, hold on, that you're doing, like Emacs, let's say. Stop Emacs, hold it. I gotta go run the code for this timer overlay that Casey wrote, right? Or something like this, if that makes sense. So if you think about what happens there, however frequently that scheduler wakes up, is the minimum amount of time you could sleep for. Because if your thread goes to sleep, it's not going to wake back up again until the scheduler comes back on the CPU and looks to see and goes, oh, he wanted to wake up in X milliseconds have elapsed, so I'll wake him up. But if the scheduler only wakes up, let's say, every 15 milliseconds, and you ask to sleep for 2 milliseconds, well, you're actually going to sleep for 15 milliseconds because the scheduler ain't going to wake up every 2 milliseconds and look. Excuse me. So we can fix this. It's not a perfect fix, but we can fix this. We can fix it with something called time begin period. Now, what time begin period is, it's a weird. I don't even want to know how this ended up being the way to do this. You can sort of see how, but oh my lord. You would think there'd be something called set scheduler granularity, but no. What actually happens is time begin period is like an old multimedia system call for setting when you would get callback timers and what resolution they had to be. And of course, the callback timers couldn't happen in the timer granularity unless the scheduler was waking up at that granularity, so it ends up setting the schedule granularity in Windows. And it's series in milliseconds, which means the schedule granularity we can set all the way down to 1 millisecond, which is fine because we're only going to sleep at a millisecond granularity anyway. I don't know if that makes sense, but hopefully it makes sense. I don't actually remember, to be honest with you, it's been a long time. I don't actually remember how you make this call. It escapes me at the moment, but we'll go ahead and put it in here. Excuse me. So basically you call time begin period and you pass it the millisecond granularity that you want. Excuse me. So basically desired scheduler millisecond, like that, is 1, just so people reading this code knows what's going on. Note, Casey, set the Windows scheduler granularity to 1 millisecond. So that our sleep can be more granular. So let's do that. So there we go. And now I just can't, the only thing I can't remember is whether you need to actually, well, you know what I think? Yeah, you know what I think? I think there is one other thing that we want to do. The memory is kind of, it jogs. I don't actually remember, let's see, if there is, I thought like there was a way we could figure out to verify that was right. Well, we can look at the H result at the very least. So if this MM result thing that comes back, if that returns time no error if successful, I like timer no can do. That's interesting. Someone had a sense of humor there. So basically if that does this, then it's okay to sleep, or I should say sleep is granular, is true. In fact, we could just do this. We could just record this like that. Rule 32, sleep is granular equals that. So there you can sort of see, I'm just basically recording whether this worked. So if it believed it could set it, then we'll set it. Now the reason that I wanted to record what it is because I don't want to introduce this sleep if the operating system isn't going to be able to do it. So basically I want to do, if sleep is granular, then allow the sleep, otherwise don't allow the sleep. Does that make sense? Now that was like I said, a multimedia function. So in order to link with that, we have to link with the multimedia library, which is pretty trivial to do and exists on all Windows. So that's not a risk. It's not a linking risk. I believe it's winmm.lib. Yeah, it is, of course. Remember, you can always determine that by going down here, but sometimes I like to see if I still remember. So, all right, now we have basically gotten that working. Our sleep should be more granular, but we still have no idea whether this is working right or not. Like, we've got no idea, and so we can't really make any conclusions yet, but we're out of time for the day. So this may be incredibly buggy, we don't know, but at least we've gone through the theory of what we're trying to do. We've started to make ourselves try to target lock to a frame rate, so that's good. And tomorrow we should be able to go through and actually clean up the audio side of things and do some testing to verify that we're actually running at the frame rate we think we are, because all of this stuff is probably buggy before we test it. So not tested yet, probably buggy. Right. So we will do that. You know what we could do as well? We could go in here as a very simple test, not a particularly great one, but we can go in here as well and turn this back on. This would give us a little bit of a sort of an idea, if you will, of what's actually going on. It would do our old printout that we had. So counter elapsed. We would just need to go like this here. Counter elapsed milliseconds per frame, like that. So the milliseconds per frame is win32 get wall clock, or sorry, get seconds elapsed, like that. 1000, like that. And then we would just do end counter, last counter, like that. So that would give us at least a little bit of an idea what's going on. We don't actually need, or do we? That's global. That's that. Counter elapsed. We don't actually have that, unfortunately. Okay, so let's get rid of the frame rate here for now. Well, that's easy for us to compute again. So let's just go ahead and zero that out. We'll do that in a second. And buffer is redefinition. We've already got a buffer. Not surprising. Let's see where that was. Buffer. Well, actually, yes, I don't care. We'll just do FPS buffer, and then we're done. So I'm just turning this on as the last little thing we do in the frames, just so we can take a look. Oh, good. It's telling us a warning about this. Well, what do you want me to use? I guess it's basically giving us a security warning here. And that security warning is because you might have a buffer overrun, which is fine, but this is debug code, so I wish it wouldn't do that. We could turn off that warning, but I believe there should be some kind of a guarded printf, you would think. Oh, it still thinks that's unsafe. What would you like me to use? _s, I guess. So you want me to use this? What do you want me to use? All right, well, hopefully that works. Basically, they try to increase security by doing these things, and they often fail, and they end up just annoying you. But, you know, they were trying. At least they were trying to do some security. So we look like we're pretty close. We've got a ways to go before we're actually really accurate. But it looks like we're sort of getting our 33.333333333. We have some reasons why we won't. Basically, the thing that we haven't done yet is we don't include this time information properly and some other various things that we're not doing properly. So there's definitely some other stuff that we want to kind of do to try and make that a little more accurate. But at the moment, it looks like we're pretty good, so we're getting there. So that's good. With that, we are now at where we should be at the Q&A, because we started 3 minutes late and it's 9:03 now. So we should be right where the Q&A should be. So let's go ahead and do some Q&A here. I'm going to open up the Twitch chat. Please make sure to put C Muratori in your question somewhere so I can see it. And please keep the questions to stuff we've done on this stream or in some previous stream, because stuff about future stuff is stuff we'll get to in the future. So, all right, let's go ahead and see what we have for questions. Let's see. If we are locking the frame rate, won't that mean that this engine will slow down the entire game if a person has a bad computer and cannot hit our frame rate? Yeah, so we're not locking the frame rate. That's kind of that's not really what we're trying to do here. What we're trying to do is run at a fixed frame rate. So what we will do as we go forward is in this code, this right here, this target hertz, we will update what the frame rate is that we're trying to hit dynamically. So that if the user has a computer that can't even hit 30 frames per second for some reason, we could drop down to 15, for example. And then the game will still run at the right speed, but the frame rate will be very slow. We could do that. Now, I would argue that we should probably just put up a big old box that says you got to buy a new computer, because you shouldn't ever run a game at 15 frames per second. It's basically unplayable. But we can decide what we want to do at that point much later down the line. But we're not saying the game has a fixed frame rate. We're saying that we're fixing the frame rate at any given time so that we know when we're going to flip so that our animation is consistent. But we can always change what that fixed frame rate is if we want to, and then the game will always use whatever we tell it is the frame rate to do its world updating. So we have the flexibility to run at 60, 30, 120, whatever we want to run at based on the speed of the end user's machine. And the game will respond accordingly. Even if you could grab the refresh rate of the monitor, how do you synchronize with it? Well, so for our prototyping engine, we won't probably bother synchronizing with it. Direct Draw actually does have a thing that allows you to wait for the vertical blank, and we could use that if we wanted to. Again, it depends if you want to use Direct Draw, which nowadays is very deprecated, unfortunately. I don't know why. It would be nice if they'd maintained it. But basically, for our prototyping layer, we probably won't sync with the monitor. So that's fine, because all that means is that we'll be like off one frame potentially, or we'll get some tearing, like a line down the middle as the frame is flipped. But when we actually go to do the final platform layer, we'll be outputting through OpenGL or Direct3D. And those have ability to set a flag that just says automatically sync, like when you do a flip it with the monitor. So we won't have to worry about that. That will just be taken care of by the operating system. When we push a frame down, it'll automatically sync to it. So we don't actually have to do that ourselves for the shipping game. Doesn't the sleep function go in the surrounding if instead of the while loop? Well, it can go either place, I should think, right? Because basically this should, I mean, one of the things we should do, obviously, we could certainly put it, well, yeah, we could certainly put it here, and you would assume that that was accurate. But really, the thing that I didn't do and need to do here is make sure that we don't bother ever calling the operating system if sleep isn't 0. So that's a bit of a mistake. And so, yeah, what the person was asking is, why don't we just do this outside? And they're totally right, we can do it outside, because there's no need to do it inside the while loop, because the second time through the while loop, sleep milliseconds is always going to be 0, presumably, assuming we actually slept for the time that we thought we were going to sleep. So, I don't know. You could put it out there, you could put it in here. It doesn't actually matter where you put it, as long as you checked the milliseconds to make sure that they're greater than 0. So, I don't know. I feel like if it's inside the while loop, it catches some problems. Like, let's say sleep doesn't sleep us for the time for some reason, because the operating system just thought it was going to just wake us up right away again for some reason. Then we just spin lock for no reason, and maybe we want to give the operating system the chance to sleep us again. So I feel a little more comfortable having it in here. Although that said, it does do one extra computation, which maybe we would argue is bad for the spin lock, so I don't know. It's really hard to say. I guess we'll leave it out for now, but I could go either way on that. And in whatever you want to do in your version of this code, does Win32 fill sound buffer need to come after the vsync loop? Yeah, well, so we need to, and I'll put in to do just so you guys know who are following along at home who might be confused about that. Okay, so basically, sound is wrong now because we haven't updated it to go with the new frame loop. So I haven't touched sound at all. So sound is just wrong. And I don't want to patch sound right now. Like, I don't want to fix this or anything. Because that's interesting. I don't know why this is a note. Should be. Oh, I guess it's just saying it's the output test. Let's get rid of that. Basically, I don't want to touch sound at all because we're going to redo how we're doing the sound timing. So I want to do that in line with the rest of it. So don't think about sound at all. We haven't looked at sound at all. It's totally wrong. And doesn't obey the diagram that I was drawing at the beginning that I said that we wanted to do. So tomorrow our job is to make sound line up with that diagram. Check DWM get composition timing info on MSDN if arrow is on. Could you explain the potential advantages or detriments to handling update and render on separate timers threads? Is there ever a good reason for a programmer to update the game state more frequently than they render it to the screen? So, no, there isn't a good reason to update the game state more often than they render it to the screen. However, there is a good reason, tightly related to that, there is a good reason why you may need to subdivide some aspects of the update into more granular updates than the rendering. And so the example of that would be, let's say that your physics time step needs to be 1/120th of a second, but your game frame rate is only 30 frames a second. well, then you kind of are in a situation where you're going to have to run the physics update more frequently. So you have to kind of run it on a subdivided time step. So there are definitely ways that you could do that with separate threads if you wanted to. There's a lot of different ways you can approach that problem, but obviously the simplest one that doesn't involve threading or any sort of stuff like that is just to run the physics in like a for-i loop inside the game update. It's basically like, we're going to do the update for the game. We need to update the physics 4 times for every one update of the game, so we just call it 4 times with a quarter of the time step, and we're done. So that definitely does happen. Whether or not you should multi-thread that and then update the game at a different time, I mean, I don't like that kind of thing, but I wouldn't necessarily say that it's wrong, because you can sort of see arguments for why you might want to do that. I mean, I don't know. I don't love it, but I would be hesitant to say that it was the wrong way to do things. It's just I don't particularly love that. So I think it adds a lot of complexity, and I'm not sure you get a lot of benefit for it. Let's see. If we are locking... No, okay, I already answered that. How would you adjust your memory management strategy for devices with limited memory? We haven't done a memory management strategy yet, so wait until we actually do our memory management, and then that should become clear, I think. Won't we miss frame rate due to the sleep because while you're truncating to millisecond, you aren't accounting for the up to 1 millisecond granularity? Would just removing 1 millisecond from the wait work? Well, I don't think so, because, I mean, basically, this is going to give us how many milliseconds to sleep, and it's going to be fractional. So this value is going to come back like 10.3 milliseconds, let's say. If we then truncate it, we get 10 milliseconds. That gives us 0.3 milliseconds of time that has to be spent spin locking. So I don't think we would miss the frame rate at all there. Now, there is a separate problem, which is that we're not accounting for the fact that if we actually were talking about doing this in sync with something, we would want to account for how long this took and wait for how much minus that. But we're encapsulating all of the time because we're using our end counter. We're always accounting for all the loop time because we're subtracting from last counter, which gets set here. So we're actually accounting for the time that it takes to flip as well. But I don't know. So I don't actually think we would need to do that. But if the sleep milliseconds actually causes us to sometimes sleep an extra millisecond, then yes, we would want to subtract that. Now, something we could do here, just for our own benefit, is assuming that we went through here and did the target seconds per frame thing and whatever, we could assert, basically, that the first time, when we actually check the time here, we could assert that it is like this, right? We could assert that test seconds elapsed per frame is greater than 0, right? Is less than target seconds, right? To assert that we didn't sleep too long, we could do that, and we can see what happens there, just to see if we ever... After we do the sleep, let's verify that we didn't like sleep past the frame time. So we didn't do the thing that you were worried about it doing. And so I don't think it's going to do that. From the readout here, you do notice that this is just not right. Like, this should be really close to 33.33, and it's not. So we still have bugs, so I don't want to say that we're not buggy. But I just don't think that thing you're talking about is actually happening, or if it is happening, it's happening in a different way. Because we are asserting this here, and we now can see that that's not actually the case, right? Hopefully that's clear what's happening there. Garlando Bloom says, shouldn't tear if we are in windowed mode, in Windows at least, unless people disable WDM Arrow. Yeah, I assume that Arrow does all of its compositing on a flip, so we shouldn't see tearing, but if you were on Windows XP, you might. I don't know. I'm not sure. It depends on the operating system and what you have. Can you fix the physics animation frame rate without fixing the graphics frame rate? So if you miss a frame, just run the physics more than once before rendering the next frame. No, that doesn't help you. You still showed the wrong thing, right? We don't have to run the physics multiple times because our physics is going to allow large time steps probably. So we'll always have the physics be able to run the right amount of time to catch up to where it thinks it should be. But just to sort of illustrate the problem here, based on what you were sort of saying, so I'm going to go ahead and clear this out. Fantastic. Of course, that's exactly what I want to do, is make it tiny for some reason. I do not understand why it did that, but that's fine. Let's go ahead and zoom back in there. Wait, oh, now the zoom is too... What? This does not look like a good program. No. Smooth draw. No. 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 Okay. Anyway, so basically what I was trying to say to that question is, let's say we're here and we've computed, you know, so we're on our fixed frame rate. So we advance the world 16 milliseconds, right? We advance the world, we plus 16 milliseconds, and that was supposed to show up here, but we missed it because we took too long and we ended up here. So it was basically a plus 16 millisecond update, and we end up with a 30 millisecond interval, right? What I'm trying to illustrate here is this is wrong no matter what now. It's just you showed a wrong frame. This frame should have been at plus 33 milliseconds in physics time, but it was actually at plus 16 milliseconds in physics time. So it's just wrong, 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 wrong. It's all wrong. It is all wrong. So what a lot of people do is exactly what you're saying, and it's totally wrong. What they do is they then go, okay, I missed that, so what I'll do is it took 33 milliseconds, so I'll make this frame add 33 milliseconds to the time. But now this frame might flip in 16. So now what you've done is you've like wronged yourself twice. This is 2x wrong, right? So this is always wrong, and no, don't, like no. Much like smooth draw is no, don't do it that way. What you need to do is try to figure out how much time you think this frame will take to draw, and that is how much you need to update your physics by. Never use the last frame's time unless you then decide that that is exactly how long you're going to gate this frame time by and you think you can hit it. Like, the previous frame's time doesn't tell you anything about this frame's time because you don't know what happened on this frame. It could have been that something unusual happened on this frame that isn't going to happen on this frame, and so they're not going to be similar times. So you need to be aware of all this stuff and make good decisions instead of just mindlessly forwarding that last frame time to this frame time, because that's just totally wrong. A lot of games do it, and it's totally wrong. It's never correct. Why are we handling sound and video differently? I'm afraid I'm not sure what that means. If you could tell me what you mean by that, I will try to answer that question. I suspect it's probably a good... Wouldn't you want to fill the screen buffer before you hit the frame flip point so that the monitor could grab the correct data when it refreshes? Well, yes, but you have to remember, we don't know when the monitor is refreshing. So all we're doing here is we're just creating a loop that will keep our game running at 30 frames a second so that all of our timing decisions will be correct. Later, when we do a Win32 layer that outputs through one of the modern graphic APIs like OpenGL or Direct3D, then that we will have a different strategy of doing exactly what you're saying, which is pushing the frame down and then waiting and letting the flip happen at the right time. But we don't even know when the flip is happening here, so we can't actually do anything about that. There's just no way. So what we'd rather do is wait the right amount of time here before, if that makes sense. But will the art and music creation be live? What do you think about having a fixed physics time unconnected to the drawn frame time by interpolating positions of objects based on their time differences? About it because I've never done it that way. There are some attractive features of it, which is that it kind of lets you have a more consistent gameplay experience potentially if it's done right, because it would allow you to make sure that the physics plays the same in some sense on all platforms, whether it's a 50 hertz, 60 hertz display, something like that. But I feel like you're doing a lot of extra weird stuff there that may actually end up giving you a worse experience because the user is putting input in at a time that actually is before the time that is the latest thing the physics already knows to be true. So the user actually now has input lag that they wouldn't have had before, and input lag is not good for a gameplay experience. So I really don't know. So I don't know. I can't speak of the variable sync stuff, but the point is never miss. Like, you should never, ever, ever miss your frame rate, or it's going to be a bad experience. Like, unless you only missed your frame rate by like a tiny, tiny fraction, in which case that maybe the user couldn't perceive. And maybe that's a good thing about those variable vsyncs is like, hey, I missed it by just a tiny, tiny amount and flip. Then that's fine. But you kind of need to make sure you never miss, just not miss at all. Like, I mean, it's not that different saying I have to hit 17 milliseconds versus 16.66666 milliseconds. So I don't really see there being that much of a difference between those two things. But, you know, it is what it is. Certainly, it's not like bad that they're doing the variable sync thing. It's always better to have a variable sync monitor because there's more you could do with it, right? It can only ever help. It's not going to hurt unless they broke something when they started doing that, right? So it is always better to have a variable sync monitor. It's just like, I just don't know if it's worth the cost or whatever. That, I mean, it eventually should presumably just be free to kind of have that logic in there or something, and then we just always want it. But it's like, do I really see much of a benefit to it? No, it's like a super, super minor incremental thing. Like, it's not a big deal, I feel like. So that's all I was trying to say about that. I'm not trying to like pessimize those monitors and try to be like, oh, they're crap. I think they are better than what we have. They're just not much better. Let's see. I think that might be all. That might be it. That might be it. Are we done with the Q&A? Is that it for Q&A? I think we may be done with the Q&A 5 minutes early. That is good stuff. That is very good stuff. All right. Well, I mean, I will wait for another minute to see if there's any last questions that have time today. So that'll be fine. So it looks like there's no something that just came in there the minute. Earlier, I watched one of Chandler Karras' talks where he describes the relationship between data structures and algorithms in the context of C++ performance. He mentioned that you could lose compiler optimizations for an object by bringing its address into its identity. Could you shed some light on exactly what this means? I'd have to go rewatch it. I'm not sure what you mean by the phrase bringing its address into its identity, but I could go watch that and we could talk about it on a future stream. So that's good. Is it worth talking about timing resolution in kernel or too deep? Well, I mean, I've never seen it. So anything that I said that was talking about the Windows kernel would kind of just be talking, hypothetically and going off of like what people post in MSDN blog posts or something. So maybe there's a good lecture out there. There might be a good lecture out there by a Windows kernel guy who talks about the timing, and we could go by that. But honestly, like, I don't really know much about the Windows kernel timing. I don't know what they do in there. I know that time begin period changes the kernel timing, but I don't actually know much more than that. Pretty sure Chandler was suggesting passing by value because the compiler had a lot of problems optimizing through pointers. Yes, that is true, but that really only helps with inlining. I think he was talking about inlining. The optimizer, you could actually make your code slower by passing things by value if it can't inline them, because it would have to actually do the copy. So basically, you have to kind of know, you kind of got to actually look at what the compiler is doing. You can't just go always pass by value, always pass by pointer or whatever. You kind of have to say, let me see this code, why is it slow, and let me see if I can make it faster by changing the way certain things are passed to it. So as a good rule of thumb, super small things always should be passed by value, obviously, because it's easy to do so. And it's like, if they're smaller than 8 bytes, then they're smaller than a pointer anyway. So you should always be passing 8-byte things by value, you would think, because passing the pointer to them takes as much space as passing them. So you're only incurring a speed hit. But things that are significantly bigger than a pointer, 64-byte things, let's say, 32-byte things. At that point, you may be getting into the territory where you have to actually know that the compiler really can optimize it before you actually get a win. So be careful, I would say, about that. That is what I would say. All right. I think we are done with questions for the day. Thank you so much for joining me, and I hope you also enjoyed John's stream earlier today. I know I did. If you would like, we started on Handmade here. Download the page, so you can go join the forums link here with our past episodes, all sorts of stuff like what the hours are going to be, information. So Pacific we can do, which I don't know how many people can make it to the 11 a.m. stream. I know.